And we didn't achieve that earlier because we do have a quantum control of these two states, but the emitters emit a different state. The coherence information between that and this all lost. Then there is another one that people have done. This is called differential transmission. Okay? And then they have done this, and in this case, they control this state. And they probe the situation of this state by sending a probe pump to look at how it is transmitted. Okay? So it's really the absorption measurement. And they never really been able to harness the emitted light. Okay, but I think if they try to do that, it will suffer exactly the same kind of problem. And then there's this other scheme, this is called by Zwener. What they did is they used the optical control to generate the exciton here. They coherent control this two-level state. But when they detect, they have a bias, so then this thing will come out, detect as an electron. This will come out, detect as a hole. They look at photocurrent to measure it. So this, its optical control is the exciton ground state. But it cannot convert that into the photon, such the photon can be the carrier. So therefore, none of this really have, and I would call control carrier. I think I have to also, there is another paper published also right around at the same time by Kamada at NEC. I think they have done this, they have seen this stress state in this emission. So you can see within 1 year, many groups achieve all the same time Rabi oscillation. Okay, 4 groups in less than 1 year. This group is the first, we're second, and then this thing is the last, but they all happen in 1 year. It is kind of, in science, you need to always know that, if you get something, okay, if anybody know that you get something, even though they didn't come and look at what you did, they can very quickly reproduce it very fast, okay, if they are active researcher. So it's like this. So this is why if you observe something spectacular, you need to publish as quickly as you can, all right? So this was my suggestion, because the other day when I listened to your group's presentation, I found there's something pretty spectacular, and you really need to publish that fast, okay? So, right, so in that year, and then these all happened 2002, 2001, 2002, and then later on we have implemented this one, we have used this to do the actual quantum algorithm, and then demonstration of 2-qubit operation, and then this is my colleague, this was when she was working at Michigan, published this C rotation, and we have done this swap rotation. It's all happened. So you can see it's pretty hard to then go from 1 qubit to qubit, okay? And I indicated none of them is really coherent control quantum emitter. Then there is another field in quantum information science in addition to this thing called quantum coherent control of 1 2-level system. It's this thing called cavity QED. And Professor Yamamoto at Stanford University is really the pioneer of quantum dot, in this field. Before that, this cavity QED, of course, was also a very important topic in atomic physics. So I want to give you a very hand-waving, description about what cavity QED is. And if you're interested, you can go read a lot of literature so you will understand things in a more complete and sophisticated way. Assuming I have a 2-level system, it's optically active, okay? So let me sort of, before we go into that, I want to ask you a question, okay? And this is for since you guys are all graduate students. So whoever answers this, I'll buy you a beer tonight. Why you got projected into this eigenstate doesn't stay there forever? because there is vacuum space and it will couple to the vacuum. Is that what you tried to say? So this state is not truly isolated from what you tried to describe, right? Very good. In fact, that is exactly the right answer because there is this vacuum exists there. So vacuum can support all kind of the photon mode. So therefore, when you have that, it sees, I can emit a photon into the vacuum and come back. So therefore, this two states can couple. So that is really define what is the radiative relaxation of a two-level atom. Now, the vacuum is allow photon mode. It has a continuous distribution, right? So the two-level atom can now emit photon into vacuum. Now, what happens if you put this atom in a cavity? So what is a cavity? Cavity, because of the space confinement, right? Then the allow photon mode is no longer continuous. It has delta function distribution, right? At discrete level. And then you can control where the photon modes are by controlling the cavity. Control the cavity length. So therefore, a cavity means you have discrete photon mode. What happens when this transition mode matches that photon mode? Then suddenly its available final state for me to decay into, its density of state increases tremendously. So it wants to relax very fast, right? And that it was first described by Purcell. Say this is what they call the Purcell effect. Okay, so if I see this photon over there, it has this delta function of density of state, then you want to emit the photon, right? And indeed, has been seen, and people, we won't cover how this cavity was made, but indeed what I have seen is that when this thing matched the cavity mode, then its relaxation time, the radiative relaxation time gets shortened very quickly. And when you're far away from it, then it starts increasing. So presumably, if you're very, very far away, then its lifetime will be very long too. So and this has been observed and has been reproduced everywhere. Then there's another regime called strong coupling regime. That is, if this cavity, is a high Q cavity. High Q cavity, what does high Q cavity mean? Photon can go in there and bounce back and forth, back and forth, back and forth before it leak out. So if that's the case, then when I emit the photon, but then this photon will go in the cavity, go back and forth, back and forth, back and forth, and live so long, I ended up, I can excite this atom, then get reabsorbed. So you ended up having this one exciton state, no photon, or no exciton, one photon state. You go back and forth between the two. That is what we call strong coupling. And you can see now, let me ask you, if I have this cavity very, very small, do you know what that means? That means this photon got to interact with this atom all the time, right? If this cavity is of the order of the photon wavelength, then it interacts with this atom all the time. So that is when you reach the highest coupling coefficient. So the coupling between the two all depend on how you design the dipole moment of your emitter and the cavity volume and also the quality factor of the cavity. And that is what people call strong coupling. Once you have that, then you have this level and this photon level, and then you create this thing called vacuum-Rabi oscillation. It's different from what I say, driven Rabi oscillation we described earlier. It's just because of vacuum field. It oscillated back and forth between the vacuum field, and that has been observed 2004. Again, this is another one that happened all at the same time. In fact, they published back-to-back in Nature. So you guys have to, the science, you have to also have your ear, your spy going everywhere. It's almost like a war, right? Okay, so that's called cavity. Quantum dot cavity, QED, has also been seen. Of course, this is again been seen first in atom. But all the demonstrations showing here, okay, when they try to create an exciton in the quantum dot, they really don't have a coherent control of it. They just create this quantum dot that this exciton go to the ground state, and then, okay, yeah, it is over there, now interact with this cavity, and let's see what happens. So they can only see this simple Rabi splitting. That's about it. Very little they can do about it. So now imagine if you can now control it. You want when it go to that. You can create a pipe house, put it over there. You will know when it to create this initialize this condition. Then you will couple to this cavity. In either a strong coupling regime or in a weaker coupling regime, they can do a lot of stuff. So now what I'm going to do is go to the main focus. We have about 30 minutes, just about enough time to go through this. So I indicated if you want to do excitation, you want to excite the thing into the excited state, then you can look at things in the emission over there. Then you will be able to see this, quantum control phenomena. And the optimal goal is this, right? Now, the laser light is very, very bright, I indicated. And this, because you can use a spectrometer to distinguish the two. Right? How is this possible? And let me just say, so the main difficulty really laser scattering. And there are many people try it out with use polarization, orthogonality, use a cross polarizer. And indeed, when we publish this paper, there's another paper published also using cross polarizer. But I will let you judge, which way is better, okay? But I want to say we borrow this from this concept from atomic physicists. In atomic physics, when they do the resonant fluorescence, what they have done is, this is the atom, and this is the cavity. The cavity will, photon either emit this way or emit that way. It depends on the reflectivity on the mirror. Okay, we'll always go to in a less reflecting direction. So if now they have a cavity, but then the cavity, they have a slight opening. So then if they just trap the atom in here, and then shine the light over there, and then let the light coming out that direction, then the scatter light, unless it's physical, like a Rayleigh scattering, like this classical scattering, otherwise the light usually will not bend direction, right? And it will just pass right through. Unused laser light will just go right through. Only those strongly interact with this atom will get absorbed. And what we've done is essentially the same. It's just a solid state analogy. Okay, so what we did was we take a gallium arsenide wafer, we grow DBR, DBR layer, then we grow quantum dot, and then we grow DBR. So we have a top mirror, bottom mirror. You can see we try to draw it as a curve because that's what we ultimately want to do. But no, not really. We really have a flat mirror, right? So when we have this material, then what we did is we cleave the sample. Then to create this edge. Now, and we make this, we mount the sample at a cold finger. Then we come out with a fiber, and then just move over here, and then we can move the fiber. If you want to use an eye to align it, it's impossible. So you just take them, and you need to be able to move them up and down, left and right. And eventually, by the time you hit right at this kind of waveguide mode, boom, you see very, very bright quantum dot emission come out, and with very little laser background. So I want to show you what you see. Okay.